Good morning. We will see the unit 5 as a design and testing. In this unit, the different process flow we have to see, and the different categories: microchip design, SOC, and ASIC design. So these are three categories that we have to look at. Next, for testing, what are the different type of testing we have? Built-in self-test, boundary scan test, like that and all. So these are the and test programs, test benches and test programs. So these are the topics in this unit 5, and you may expect any questions SOC and chip fabrication and ASIC design flow. If these are common, only the uh, little changes will be there. So normal IC fabrication process, all the steps will be there. Microchip design, the size will be of the micrometer, so that we have to scale down all the parameters. That's the microchip design. And SoC, semiconductor on chip, so the chip has to be constructed over the semiconductor. So this is the logic for that. The procedures are the same. Again, the design process is the same, but in case of ASIC, application specific integrated circuits, so it has to be, the IC should has to be designed for a particular specific application and all. So for that, what are the steps has to be followed? It has to be included additional. So this is how you have to write it. And so any topic may come. So the things are same, fabrication process are same, only the designs, additional steps we have to include for everyone. So for microchip we have to write some specific steps, and for embedded cores and SOCs we have to write specific points for that. And for ASIC also we have to give the specific for points for that ASIC design. Okay. Okay, we will move on to, so the 2 marks may be expected from what are the different models, fault models, and what are the different types of scanning, and what is the definition for scan design, boundary scan design, and what is the definition for built-in self-test, and what is the ATPG, automatic test pattern generation. It may be these may be the questions. And what is the difficulties in microchip design, and what may be the difficulties in SOC, and what are the steps to be considered for the ASIC design. So these are the important 2 marks for these question topics for this unit. Okay, move on to the topics. So introduction, wafer, this is the general process, fabrication process. So first of all we have to prepare the, we have to choose the silicon dioxide, that is pure sand, and that we have to melt it with a high melting point, like 4000 degrees Celsius, like that and all. And it will become a, molten liquid that has to be solidified into a rod. So this is, we call that to be a ingot. So we have to solidify this into a cylindrical rod, that we call this as a ingot. Okay. So this ingot has to be prepared. After that it has to be sliced. So this is the wafer. So this is the first step, wafer preparation. So in the wafer preparation, these are the steps. So, pure sand has to be melted into a solidified rod, ingot, and these ingot has to be sliced with the machines, heavy accuracy machines, with a mirror of very minute size of like that, 1 like that. It has to be selected. So this is the less than because the size will be nanometer, micrometer and all. So it has to be less than So this is the wafer preparation step. Next preparation, this is the wafer preparation steps. So this is here, they have shown here the ingot. So here the pure metal seed crystal has been melted, and the ingot has been prepared, and say it has been sliced for the wafers. Here you can see the slicing, wafer slicing. Next step is oxidation. The wafer has to be coated with oxide layer. So here we have so many oxidation methods. MCVD, so many oxidation methods are there. Modified chemical vaporization and decomposition, and plasma PCVD, plasma oxidation, like that and all. So many techniques are there. If you search in Google what are the different types of oxidation techniques for the silicon wafer preparation, you may find 3 to 4 techniques are there. The isolation, we need to separate each box, each regions. So that is isolation. So next is the insulate. This is the trench. This is for the making the well and all. And for making these trench, it has to be, and the mass has to be generated and it has to be cut. So this region has to be excavated. Means that is a mass has to be generated. That is mass generation step. And these the regions exposed to direct sunlight uh, will be excavated, because these will be get molten and it can be easily trimmed off or excavated. So this is the way how it has been. So for applying the for generating the mask, we call that to be a photolithography, since we are excavating the material with the help of a light, UV light. So photolithography. Now after creating the wells, and the regions has to be diffused. Right? These regions. So we have separated these regions. Three regions we have separated. So P region and these two regions where we have separated. We may diffuse different charges. We may implant positive charges or negative charges to make this as P region or N region. If we increase the deposit, if we increase the doping concentration, we can move it to P plus or N plus regions. So with this, we will be finding in the N mass and P mass transistors where your drain and source regions will be indicated as plus. So that indicates higher concentration. So this is the next step, diffusion. Introducing the ions is called the diffusion process. So after that, deposition. So polysilicon we have to deposit for making the gate the next was well and channel formation, and next one will be the gate and source drain formations. Next will be the contact, so source and drain that we are making. We are making the diffusion of n and n plus regions and substrate. We will be for constructing a, if you are constructing a PMAS means, the substrate should be NMAS. So on a NMAS layer, we will be making a drench, and we will be introducing the P plus regions, P plus ions in the two ends that will act as a source and drain. So that will be, will be the construction of a PMAS, and the channel will be P type channel. Okay, the substrate will be N type. So this is how a PMAS transistor has to be constructed. And if we have well within a well, we call to be a double well or triple well process and all. Next, passivation, we have to separate the terminals at all separately. Next will be the casing. So this will be the general fabrication steps. This will be common for the semiconductor microchip design, SoC, and ASIC design. But the design procedure, the earlier design steps will be different. So for microchip designs, you have to consider the dimensions in the case of in the level in the range of micrometer. For so P well process. So you can see the well process. This is the steps. So addition to the fabrication process, you have to make this. Here also the same formation of N well regions, PMAS have formation of NMAS and PMAS regions, and gate oxide layer, and pattern and polysilicon, P plus and diffusions, contact cuts, deposit in pattern metallization. That is, we are connecting with the leads, and over glass with cuts are bonding pads. This is for the plastic case for the production. Okay, the twin tub, you can see the twin tub here. So you can see in this diagram P tub. In the P tub you have both N plus regions and the P plus regions. N tub we have be having a P type regions. So here you can see, so this is a deep N well. Inside another well is being created, P well. So P well, uh, so you'll be having a P plus regions. N regions are being again diffused inside. So opposite layer diffusion is possible easier. So if we want to have the introduction of N plus, then the well should be of P plus. Okay, again, so this entire P regions is deposited inside the T plane well. So this is double well process, triple well process. Again, this is another well, right? So single well, second well, third well. So triple well process it is. And microchip design flow, you can see the diagram here. It is not clear. If you have taken it with clear xerox means it will be okay. It is not fine here. So system specifications, what are the requirements needed, and design steps. Hmm. In partitioning of the hardware and pathware synthesis, the deciding factor where we can place these devices, chip plan and design, and functional verification, timing verifications, we can verify the functions like that or not. These are the steps. So the system level verification, so this is the steps followed in a step down, top down approach in a microchip design procedures. Another procedure is the bottom up verification, reverse flow, design files, front end acceptance, reverse flow. It is. So if you want to test the functional before starting the continuous production, because if we produce a long, it will be a wastage, right? So before running in a long production scale, then it will be tested. The single device will be tested for the functionality. So if it is okay, then they will start the production. So this is the purpose of testing. So built-in self-test, you will be having the test within the same block. And boundary scanning, it will be scanning the levels. So the different types of faults will be there: physical fault, logical fault, degradation fault, parametric fault. And these are the different types of fault models. Physical fault, and that can be mapped to the logical fault. Logical fault is again to class of classes. Degradation fault, this degrades the performance of the chip. Fatal fault, this will delete the device into complete fault. And delay fault, open circuit faults. These are the different types of fault models we have. Test coding. Okay, automatic test pattern generation, this is the test pattern tool to check the design flow. In ASIC design flow, this is the design flow. So design entry, we start with the design requirements, then we have to synthesize our logic using logic gates, and we have to partition the hardware and software part. And flow plan, we have to do flow plan in the sense where the devices come, which flow. If we have a multi-layer devices means we have to play. Next we have to place the closer devices, that is placement. And routing, we are connecting the interconnect, we are interconnecting all the devices, that is called routing. And circuit extraction, so these. And post layout simulation, after that, um, um, after the arrangement, we have the post layout simulation. Earlier, before the simulation and all, layout, before for doing the layout, we can also do the simulation. So that is pre layout simulation. So this is the design flow for the ASIC. Okay, I hope you will be very clear with the first unit. Already I have discussed the two mass, important two mass of this unit. Okay, design steps of ASIC and design steps of full custom. What is full custom and semi custom? If you are able to customize our design fully, then we call that to be a full custom design. And partially, if you are able to alter means, then it is semi custom design. Okay, friends, thank you.